In this video, we'll be looking at the division of polynomials. This is when you have one polynomial, you're dividing it by another. So let's take, for example, 2x squared minus 3x plus 4 and x plus 2. Then we can go 2x squared minus 3x plus 4 over x plus 2. And so we need to be able to know what the result is and what this result means. The question typically won't be calculate this. So question like calculate whatever the polynomial is over another polynomial, and you just have to say the result. But rather, it's very useful for graphing and for factorizing an expression and factorizing a polynomial. So you'll have to use it, and you have to know how to divide polynomials. However, the question itself won't typically be divide this polynomial by this other one. So when you divide one polynomial by another, you get a answer in this form. So this is sort of thought about as a definition with regards to what the terms are called and what it sort of looks like. However, we can just think about it as px is a polynomial and dx is a polynomial. So px over dx could look something like 2x to the 3 minus 9x minus 4 over x minus 3. And at the top you have the numerator and the bottom you have the denominator. So the top you can just think about it as like the polynomial, the top one, and then the bottom we're calling the divisor. Then when we divide those two, we're going to get two separate terms. So the first term is called the quotient. So this gives us a polynomial. So the first term is a polynomial by itself. And then the second term is a polynomial over another polynomial, so another fraction. However, the Rx is called the remainder. So that's the remainder, and that is often just a constant. So often a constant. And then the dx down the bottom is just the divisor once again. So it's the same term, but over here. So it's the polynomial, so the new one, the quotient, plus the remainder over the divisor, so whatever the original polynomial you were dividing is. And so that's a general sort of form, and it's often called a proper fraction, so that this polynomial over this polynomial, and then if you put in this form will be called the proper fraction. So relating this to a numerical example, you'll see how this formula does work. So 16 over 3 is equal to 15 over 3 plus 1 over 3. Now these technically are polynomials, as 16 x to the 0 is still a polynomial. However, when we're normally talking about division of polynomials, we're talking about larger numbers. But you can see from these integer fractions how this formula does work. So you have 16 on 3 is equal to 15 on 3 plus 1 over 3. And you should see that 15 plus 1 is equal to 16, and you're both dividing by 3. Now 15 on 3 is equal to 5. Then we get plus 1 on 3. And you can see how this is. You have 16 on 3, and what I've done is I've split it into what's the highest number that's divisible by this number. So that's going to give me qx. And that's going to give me an actual integer, or in cases of generally polynomial, an actual polynomial. Then I have the remainder, so that's hence why this term is called the remainder. So what's left over, and that's divided by the original number. So you could think of it, write this as 5 remainder 1, which is technically 5 plus 1 over 3. So to solve a question such as this, you have to use long division. Use long division, then you'll be able to find the remainder and the quotient, and from those you sub it into the formula, and you can get what this will be as a proper fraction. Now, if you are going to do this by calculator, so typically a CAS calculator, then if you put this such as solve, the solve function, and you put that in, so ... then it may say that not enough variables or some form of error. And if you just put that function in straight away and then you press equals, it will just give you the same function. So typically you have to find the function called a proper fraction, or it may be called something different depending on the calculator being used. However, it is in normally like an algebra sort of section, and you can put proper fraction in dot dot dot, and it'll give it in the form qx plus the remainder over dx, which is what you want, the useful form for calculating. So when we have to put this into a long division, so how do we set up this equation? So I set up like this. So you have x plus 3, and then you have this is being divided by the numerator is being divided by x plus 3. So the numerator is x to the 5. However, this is slightly different to the equation up there, and that's because I put in these 0 terms. As the polynomial doesn't have any x, or has a 0x to the 4 term, so that just is equal to 0, and a 0x to the 2 term, which is just equal to 0. And then you can just leave them out for simplicity. However, with long division, if you leave them out, that's fine. However, it is a lot easier to make mistakes, so I find it is better, and you're less likely to make numerical mistakes if you put in these 0 terms. So we'll solve this long division. So we have x plus 3 over x plus 5. So the first term is x to the 4. And that's because you've gone x to the 5 over x, which is just equal to x to the 4. So all this time you're going to have to divide by x over every term. So that's just long division. Then we get this term, we times it, and whatever the result is, we're going to minus it from the first 2 terms. So we have minus x to the 5 plus 3x to the 4. Now I always put the brackets and then put a minus on the outside, as when you have minuses, so two negatives make a positive, so it is often easier to put a negative out the outside, negative in the inside, and then you'll realize that it will make a positive. So this is equal to these cancel out, and then we have just negative 3x to the 4. And that's because you have 0x to the 4 here, but obviously it's 0, so you're just going to have what this result is. This will give us negative 3x to the 3. And that's 3 rather than 4 because you have to divide by x once again. Then you times these. So you can draw a line, whatever notation you find is best to reduce your algebraic errors. And you get negative 3x to the 4. No, that's not plus, that's a minus 9x to the 3. And you can see from the negative, negative, negative that they're all going to be positive. So we'll do up this term up here. We'll bring the negative 3x to the 3 down. We find that negative plus positive cancel out. And then a negative with positive 9 will give us 6x to the 3. Then we bring that up. We get plus 6x squared. And once again, you repeat the process, bringing that down, plus 0x squared, minusing from 6x cubed plus 18x squared, and we get negative 18x squared, which will go up here, negative 18x. Continuing the calculation, we have negative 18x squared, then that turns into negative 18x plus 4x, so we're bringing that term down, minusing that from negative 18x minus 18 times 3, so that's 54, 4x. And you can always check at every step that whatever this term is here must cancel out with this one by calculation, because with this you're dividing by x and then you're timesing by x, so these terms have to cancel out, which they do. And then 4x plus 54x, so it's going to give us 58x. That's going to give us plus 58. And then I'll just go up here because we're going to run out of room. So 58x plus 3 minus 58x minus 174. Then it becomes, that's a positive here, because 58 times 3 is positive. So you have 58x plus 174. Then the minus becomes minus 174 plus 3, which gives us a negative 171. Our remainder is equal to negative 171. Then we find that we have our quotient up here, which is equal to this polynomial. So you should be familiar with long division. If you're not, then go back and revise it, as it is very useful. And then now that we've had these two terms, we found the remainder, so that's the very last number, and then we found the quotient. So we can express it as a proper fraction. So here is the fraction written in the proper fraction form.